Hello everyone, let's begin this presentation with chapter 1, which is Introduction to Methanol. Okay, first thing first, we have to understand what is methanol. There's multiple names for methanol, which is one of the example is methyl alcohol. One of the fun fact is that it is called wood alcohol because it is produced in a massive scale back in the 19th centuries using the destructive distillation of wood. What kind of chemical methanol is? It is a chemical polar substance. An organic compound consists of methyl group CH3 and also hydroxy group. This gives us the combination of chemical formula CH3OH. It has multiple chemical properties such as colorless, volatile, flammable, as well as lightweight. Okay, why understanding methanol is important for this project? Because we are using steam reforming process. Is applied in order to produce high purity methanol. Okay. In the market analysis of methanol, most of the part is based on reference. One of the report in 2019 by the methanol market size reported that the global methanol market are forecasted to grow at a compound annual growth rate CAGR of 9.8% from 2019 to 2026, which is quite a lot. So the assumed plant capacity, we will be following a reference which is 1.7 million tons per annum by the production capacity of a government-owned company, Sarawak Petchem, in Sarawak. Okay, now let's proceed to chapter 2.
Hi, my name is Farhana Binti Faizal and I will be explaining about chapter 2 of this integrated design project of our group. Chapter 2 is a summarization of process flow diagram, or also called as PFD. PFD indicates the general flow of plant processes and equipments, however it does not show minor details such as piping details and designations. Our PFD also includes mass fractions that we have calculated through mass balance in order to achieve our plant capacity, which is 1.7 million ton per year. Now, I will be giving a brief explanation of our process flow diagram. As can be seen from the diagram, steam and methane in vapor phase enters a unit called reforming reactor to undergo a process called steam reforming. This particular process will produce few components such as carbon monoxide, carbon dioxide, and hydrogen. However, this reactor does not react steam and methane 100%. Hence, steam and methane are also considered as the output of this unit. Then, they will continue to enter a condenser. In this condenser, steam is converted in liquid to remove excess water, which is 95%, through the bottom stream, and the remaining will pass to the next unit as stream 5. So, after that, stream 5 enters a unit named methanol reactor. In this reactor, methanol is formed between two reactions. The first reaction would be between carbon monoxide and hydrogen, and the second one is between carbon dioxide with hydrogen. Since all of the components are still in vapor phase, they will then continue to enter cooler and system recovery unit. Cooler main function is to cool down the components to their saturation point of methanol before being fed into syngas recovery unit. In this unit, 90% of carbon monoxide and hydrogen gas will be recovered and recycled back into the methanol reactor, while the remaining 10% will be discarded. The bottom product would be leaving as methanol and water only. Lastly, the methanol and water from stream 10 will enter a methanol purification unit to purify the methanol according to the specification required, which is 95% purity. Therefore, 95% pure methanol becomes the overhead product, while the remaining becomes the bottom products as wastewater treatment. They will undergo a few recycling of flow by reboiler and condenser to increase the efficiency of production, of purified methanol and reduces the amount of impurified methanol. Hence, this is the overall flow of processes.
Next is Chapter 3, Chemical Engineering Thermodynamics. I am Husnia, and from this chapter I will explain question A and B. From the question, we need to analyze vapor-liquid equilibrium graph of the mixture D103. On this slide, we are looking at XY plot. The left-hand side is graph generated from HiC software at temperature 60 degrees Celsius, while the right-hand side is graph from experimental data from Dortmund data bank at temperature 49 degrees Celsius. Both graphs have the same pattern, although they have different temperature. When X methanol increased, the Y methanol also increased and producing a curve until the mole fraction reach 1. The curve for experimental data is not very smooth and it might caused by the error during the experiment. In addition, it can be seen that Y methanol is higher than X methanol at equilibrium due to its chemical properties, which is more volatile than water. Moving on to the PXY plot, same like before, this is graph from HiCs and this is graph from experimental data. We look at the red line graph. Both graphs have the same pattern too. The upper line is the bubble point curve, while the lower line is a dew point curve. At equilibrium, the bubble point for methanol water is higher than dew point due to its volatilities and Raoult's law. From this plot, we can determine the saturation pressure and the phase for the binary mixture. The saturation pressure can be obtained when the curve is intersect at the y-axis, and like this case, this is 20 kPa. For the phase, for the binary mixture, the upper region is for the subcooled liquid phase. In the between of the line is the liquid vapor phase, and the lower region is for the superheated vapor phase. For question B, we need to construct phase envelope of mixture D103. We construct the envelope type PT from the HiC software. As you can see here, when the temperature increase, the pressure also increase.
I'm Wong Yi Lin. I would like to present about Part C of Chapter 3, Mole fraction of vapor over liquid, vapor composition and liquid composition for stream X3. We assume the basis of max flow rate equals to 100 kg mole per hour. Figure C.1 is the equipment cooler and equipment separator used for flash distillation. For analysis, at stream 3, we assume the temperature is 700 degrees Celsius, pressure is 1500 kilopascal, and the molar flow is 100 kg mole per hour. Assumptions of temperature and pressure are ranged from 700 to 1000 degrees Celsius and 3 to 25 bar. Since the temperature and pressure is high, so all the components are in the vapor phase. So before the components enter a separator, we need to control the temperature by passing it through a condenser until the temperature decreases to 43.5 degrees Celsius. While at the same time we remain the pressure constant at 1500 kilopascal. This is because condensation will happen where the water vapor will be compressed to liquid phase at high pressure. Mass flow of water is originally 206.8154 kg per hour at stream 3, and after passing through the condenser it reduces to 196.5626 kg per hour, where we are able to achieve 95% removal of the excess water later. Now, all the components in X3A exist in vapor phase and aqueous phase, where both are being mixed. Hence, a separator is required to carry out the separation process of liquid and vapor. Molar flow of stream 5 is 89.09 kg mole per hour, and molar flow of stream 4 is 10.91 kg per hour. Equipment cooler and equipment separator are the operation unit that have been used for flash distillation. Mole fraction of vapor over liquid of the stream S3 is 8.17. Vapor composition of the stream 3 is 0.0402 mole of methane, 0.0064 mole of water, 0.1827 mole of oil, carbon monoxide, 0.0457 mole of carbon dioxide, and 0.7251 mole of hydrogen. liquid composition X1 of the string S3 is 0.0008 mole of water and 0.0002 mole of carbon dioxide.
Hi, my name is Darrence and I'm from group 13. I would be the one to briefly explain about chapter 4, which is separation process 1. So without further ado, let us begin. Okay, before we start our calculation, we assume some of the stuff. So these are our assumptions, which is the methanol to be F and water to be B. And then we assume the pressure of the system to be in between dew pressure and bubble pressure. And besides that, we assume it to be the binary system, two-phase system, liquid and vapor mixture system. And this is our design for the calculation column. The next one would be our calculation. From the project that were given to us, the temperature inlet is 60 degrees Celsius and the feed line would be 0.97. So by using Atoin equation, we found out that the saturated methanol pressure is 83.9291 kilopascal and the water would be 20.007 kilopascal. And then before we can find our K value, we need to find the bubble point pressure and the dew point pressure by using their own respective equation. So the bubble pressure is 79.2244 kilopascal and the pressure of the dew pressure is 67.9505 kilopascal. And then since we found out the both pressure, so we can assume that our pressure of the system to be 70 kilopascal. And we can find our K value, and the K value of methanol is 1.199 and the K value of water is 0.286. And then to find Q, we have to substitute all the information into this equation. And then we found out that V is equal to 0.94. And then since L plus V is equal to 1, so L is equal to 0.06. And Q is equal to L, and L is equal to 0.06. So besides that, we can find our relative volatility, alpha, which is we divide the K value of methanol over water. And then we found out the alpha value, which is 4.192. And then from there, we can substitute alpha value into this equation and we can find our curved line. So in this table, we assume the line to be curved. So we substitute 0, 0.2, 0.4, 0.6, 0.8, and 1 for the X value to find Y value. And then besides that, we need to find feed line or the Q line by using this equation, which is Y equal to Q over Q minus 1 times X minus XF over Q minus 1. And then we found out that the feed line equation is Y equal to negative 0.0638X plus 0.9855. And then we want to plot the graph, so when X is equal to 0, Y is equal to 0.9855, and when X is equal to 0.4, Y is equal to 0.9600. So from this equation, we plotted the graph, and then from the graph as well, we can find the R minimum, which is 0.1212. And then from there, we can find the R average graph. So the R average is 0.1636. Okay, from the value that we find, we also plotted 5 graphs, which is 5 trials. Okay, so we have come from the graph that we already did. We have come to the conclusion that the most optimal reflux ratio would be 0.1636. These are average creating the least stages, which is 4.5 stages, and this allows us to reduce the total cost of the operation per year, because the higher the number of stages, the more the cost of the operation. So we avoid the high operation cost, so we estimated the number of trays, theoretical trays needed is 4.5 trays, which is 3.5 trays plus 1 reboiler. I think that's all from my part. Thank you.